So I'm going to give a brief view on the revisions that I made. All of this I recorded and explained my solution right now, and I'm posting it on YouTube for the first three IQEs. I couldn't figure out how to create a video and post it on YouTube, but I took some time and I figured it out. So for the first IQE, I recalculated the volume and the force of the solution. The rubric stated that the depth distance seemed to be too deep, and that's because I calculated with the wrong volume, which resulted in the wrong density. I also redid the conceptual question to be more complex while incorporating Archimedes Law. I used the standard atmospheric pressure at sea level, which is 1 atmosphere, or all the other correct conversions of 1 atmosphere, and it is not 28 kPa as stated in my rubric. For IQE number 2, I switched the diameters that I used to find the volumetric flow rate to the fluid coming out of the tapered spout and not just the fluid before the tapered spout, because conceptually that is where the fluid is coming out from. I also found the molar mass and mass flow rate of the fluid, and I added the assumption that fluid was incompressible. For IQE 3, I reworked the conceptual question to better understand how to get the head loss in the swimming pool. It was shown that the height showed minimal head loss of the pump, which was previously discussed with Dr. Gardner in one of her office hours, that it would show that there would be minimal head loss or no head loss at all. It would be the same as the pump work. And I also recorded and explained the solution. For IQE number 4, I recalculated the x direction with angular momentum. I added the calculation where gravity is multiplied by the pressure and the angular velocity. There wasn't very much to say with this, so it kind of made it difficult to find out what was wrong. In my rubric, there was only points, but it never made comments, so I didn't know exactly what I needed to change. These revisions are also on the paper solution, so I just created a table. For IQE number 1, the Hydrostatics and Archimedes Law, I did a red and white bobber. And you're going on a fishing trip. The fishing line is 6 centimeters below the water, and after that, a 25 kilogram catfish hooks your bait and the bobber goes underwater. So for my conceptual question, why is there more pressure on the bobber when it is submerged underwater than when it is floating on the surface of the water? And I said the buoyant force of the bobber underwater has other forces as well that are acting on it. The bobber is being compressed by the forces of the water, which adds a downward force to the bobber that is greater than the upward force. Therefore, the sum of the forces down does not equal the sum of the forces up, which is why there is more pressure on the bobber when it's submerged. So for the calculation question, I have all of the information in the calculation question. I kind of want to go into what I did for my solution to get what the force is and how far does the bobber submerged underwater with a 25 kilogram catfish. So for my solution, the knowns is that we know that the diameter of the bobber is 1.75 inches and the fishing line with the hook is 0.06 meters. You can assume that the weight of the hook itself is negligible and can be added to the cowfish sliver, so it's 5.25 milligrams together. We know we need to find the force of the bobber before it's being submerged. We can assume that there is no drag, and the properties are the density of water, which is 100 kilograms per meter cubed, and the density of air is 1.16 kilograms per meter cubed, which is stated in the question above. The gravity is 9.81 meters, and so for my solution, I ended up doing volume equals 4/3 pi r cubed to get 370.406 centimeters cubed, which then we would have to convert to meters, which is 3.704 times 10 to the -4 meters cubed, making sure that we have enough significant figures before getting the final solution. For the force of the bobber, you would have to multiply the density times the gravity times the volume of the bobber itself. So it's 100 kilograms per meter cubed times 9.8 meters per second cubed times the 3.704 times 10 to the negative 4th meter cubed, which creates a force of 3.634 newtons. For part B, the known is that we know that the bobber is open to atmosphere, so P, the P atmosphere is 1 atmosphere, and then it is 6 centimeters above or below in the water, which is your height, and we're adding 24 kilograms to 5.2 milligrams. We are trying to find the height / the depth of the bobber in meters. We can assume that the density equals mass divided by volume, and there's no movement, so velocity equals zero, and the acceleration due to gravity is 9.8 meters per second squared. So the solution I did is mf plus ma equals 25 kilograms plus the 5.2 milligrams, which is approximately 25 kilograms, since 5.2 milligrams is not as significant as the 25 kilograms of the fish. So for the force of the fish, it's mass times acceleration due to gravity, which is 25 kilograms times 9.81 meters per second squared. Then we would do the density of the bobber, which is the 0.7 kilograms over the 3.704 times 10 to the negative 4 meters cubed to get a density of 0.18898 kilograms per meter cubed. We then would get a force of 245.25 newtons. I keep doing that. Sorry. We would use the Archimedes Law to find the height of the submerged bobber. So the density of water times the force of the fish times gravity over height equals the density of the bobber times the force of the fish times gravity times x plus the height. The density of water, then we can reduce this equation, which is the density of water times h equals the density of the bobber times x plus h, to get x equals the density of the bobber over the density of water times h minus 1. When we get that, we get that the height of the bobber being submerged is 1.1339 times 10 to the negative 5th meters, which equals 1.13 times 10 to the negative 5th meters, which is significantly smaller than the 69 meters that I originally calculated. For IQE number 2, the Bernoulli equation, I used a bartending scenario. So the bartending scenario, we want to determine the volumetric flow rate of the liquor through the pouring spout. We want to determine the mass flow rate and the mole flow rate of the liquor of the pouring spout, and then we want to determine the pressure within the shot glass if the pressure within the liquor bottle is 12 kPa. The conceptual question is, the bartender is quite experienced with tricks and creates a cyclone inside the bottle with the velocity exiting the pouring spout to be greater than, less than, or equal to the velocity inside the bottle. With that, it is the exiting velocity from the bottle will be greater than the velocity inside the bottle because the bottle has a greater area / volume than the pouring spout of the bottle, thus creating a velocity that is negligible inside the bottle. In a steady flow, the sum of the kinetic energy, potential energy, and internal energy remains constant, thus increasing the speed through the pouring spout. For the calculation question, our knowns is that the diameter of the bottle nose of the bottle is 2.3 0.375 inches, and the diameter of the taper spout is 0.25 inches. The volume of the shot glass is 44.36 milliliters. We can assume no friction, no work. It's an incompressible fluid. It's at steady state, and there's a constant density and gravity. The properties is that the density of the strawberry liquor is 1.12 kilograms per meter cubed. And for part A, we're finding the volumetric flow rate. So it's V dot, which is the volumetric flow rate, equals the area times the velocity average. And area is pi d squared over 4, which we're doing the taper spout diameter instead of the diameter of the bottled nose. It is, so when we do that, it is 3.4088 times 10 to the negative 4th feet squared. We can convert that into liters per second, or then we can multiply it by our velocity average, which equals 7.8403 times 10 to the negative 7 feet cubes per second. Then we can convert it to liters per second with the conversions of 28.31. For B, we're trying to find the mass flow rate and the molar flow rate in moles per second and kilograms per second. So we know that the density of the strawberry liquor is 1.12 kilograms per meter cubed. We can multiply by the simple conversion that it is 998.2 kilograms per meters cubed equals 55.5 moles per liter. Then we can get a density of 0.062 moles per liter. For the density, we already know the density of it. So we know that its mass flow rate equals density times volumetric flow rate, and then molar flow rate is density times volumetric flow rate. So when we do that calculation, we get 2.43 times 10 to the negative 8 kilograms per second, and then 1.376 times 10 to the negative 6 moles per second. For pressure, for C, pressure in the shot glass and kPa, we would use the Bernoulli equation, the extended Bernoulli equation, which is change in P pressure over density plus gravity times height plus the kinetic energy, which is velocity squared over 2, plus the friction, and then the work of the system. We know that there's no friction, and we know that there's no work because it wasn't stated in the question. And so when we write out the extended or Bernoulli, we know that the height of Z1, there's no height. There's also no height at GZ2. And the velocity 2 is 0 because it's constant flow rate throughout the spout. When we do that and we simplify it, we can multiply each side by density to get P1 plus V1 squared over 2 over times rho equals P2, which is 12 kPa plus 7.01 times 10 to the negative 4 meters per second squared over 2 times 1.12 kilograms per meter cubed. To get approximately 12 kPa, so we can assume that the pressure in the shot glass is negligible to the pressure in the water or in the tapered spout. For IQE 3, I did a swimming pool problem, and my conceptual question is, why can't point 2 pressure be depicted in the picture be solved with P1 plus rho GH at point, and point 3 cannot? And just the clarification, this is what I am talking about. Why can the pressure here be P1 plus rho GH, but this pressure cannot be P1 plus rho GH because they're both on the ground of the swimming pool? With that being said, this is because point 2 is an aerostatic pressure, hydrostatic pressure, so we can involve the pressure at point 1. Point 3 would be a constant pressure because water is moving down the drain, and at that moment of time, pressure can be assumed negligible, which can go to 0 since it's constantly moving down that drain or that pump pipe. So for the calculation question, this is all stated in the question itself. So we know that the diameter of the drain is 0.196 meters. The power of the pump is 0.0013889 kilowatts. And we know that the height at point 1 is 3.6576 meters, and the height at point 4 is 1.83 meters, and the height at point 2 and 3 is 0 meters. Just a quick note, these are not different pumps. They're the same pump at different positions. I just didn't want to keep redrawing that. We want to find the head loss at point 1, point 3, and point 4 in meters. We can assume steady state, constant gravity and density, constant pressure flowing down the drain, through the drain, input back into the swimming pool. And there's no turbine work. It's an incompressible fluid. P1 is open to atmosphere, so it's 1 atmosphere. And our properties is that the density of water is 1,000 kilograms per meter cubed. So the solution is at the top of the swimming pool. We can do the extended Bernoulli equation from 1 to 3. We know we can cross out the hydrostatic velocity because it's 0. There's no there's no velocity. There's no height at Z3. It's 0 at V3 because of constant velocity going through the pipe, and there's no turbine, so we can cross out the turbine. We can't cross out the friction because there's some friction going on, and we can't cross out the pump because there is pump work happening in this problem. So when we can do that, so power is just the mass flow rate times dW dm of the pump, which is the work, which can be converted to power over mass flow rate, which equals 4.6296 times 10 to the negative 5th kilowatts per kilogram per second, which then equals 0.0462967 meters squared over second squared. We know that the mass flow rate is density over the volumetric flow rate, which we can get 30 kilograms per second, which is put into this equation. We know that the pressure of 1 is 1 atmosphere, and then we can multiply rho g throughout, our g and rho throughout. So we get 3.6576 meters plus the 0.0629667, which is the power, over 9.81 to equal the head loss, which is 3.66 meters, and that is the same height as the top of the pool. We can do the same thing for the middle of the swimming pool. If I stop moving, we know that P4 is P1 plus rho GH. We know that the volumetric flow rate is at a constant flow because it's exiting a pipe and it's going into a larger area. It's going into a larger volume. We know that P3 is constant because of constant flow through the pipe, as explained in the conceptual question. We know that there's no height at Z3 and there's no turbine. So we reduce the Bernoulli equation to equal P1 plus Z4 plus 1 over G times the work equals the head loss. So Z4 plus 1 over G times the work equals the head loss. So we have 1.83 meters for Z4 plus the same thing that we calculated in part 1 for the head loss to equal 1.8347 meters, which is the same height as the middle of the pool. For part 3, the bottom of the swimming pool, there's a lot you can cross off because it's at the bottom. So we end up with 1 over G times the work plus Z3. So we know that Z3 is 0 meters, and this is 0.0047 meters, which is approximately 0 meters. There's no change in height with the head loss. So the pump work and the head loss are very equivalent in this problem. For IQE number 4, I did an oxygen tank sitting on a ground. I kind of wanted to make it a little bit different. For the conceptual question of this, is there a greater force acting within the tank or within the hose when the valve of the oxygen tank is closed off? is there a greater force acting within the tank or within the hose when the valve of the oxygen tank is opened, allowing air to flow into the hose? There is a greater force acting within the tank when the valve of the oxygen tank is closed off. This is because the only force acting on the hose would be the force of the gravity and the force of the ground. The tank has the pressure force of the mass of oxygen inside the tank when the valve of the oxygen tank is turned on and flows through the hose. There are direction forces acting on the hose, thus creating a greater force within the hose than within the tank. So for the calculation question, I created my knowns, the same KFAPs that I've been using from IQE 1 to IQE 4. So we know that the volumetric flow rate coming to the hose is 3 liters per minute. The diameter is 0.5 centimeters, which equals 0.05 meters. This is all in, the knowns are all in the calculation question that I stated within this PDF. We know that the volumetric flow, or the volume of the tank is 1.13 liters of oxygen, which is pure, and the height is 0.216 meters. These are all real numbers. They're not fake. I didn't make them up. We want to find the inlet pressure, PA, and the X direction, or FX, the force of the connection valve. We can assume that it's at steady state, constant density and gravity, no turbine work, no pump work, no friction work, and beta equals 1. P2 is open to atmosphere, so it equals atmosphere. The properties is the density of O2, which is 1.429 kilograms per meter cube. And my solution for pressure A, for part A, the pressure inlet, we wanted to do the extended Bernoulli equation, which P1 goes to P1 gravity. We can cross that off. We can cross off the no pump work, the work of the pump to no pump work, the height of Z2, and the work of the turbine, because there's no turbine, and then we can cross off the friction term. We want to find the velocity of 1 and 2, points 1 and 2, so it's the volumetric flow rate over A2 for V2, and the volumetric flow rate over A1 for V1. A1 is 0.01963 meters squared, and A2 is 3.14159 times 10 to the negative 4th meters squared. We can plug that in with the volumetric flow rate at being 5 times 5 to the negative 5 meters cubed per second to get V2 as 0.159 meters per second and V1 as 0.025 meters per second. We know that we can find the mass flow rate from the density and the volumetric flow rate. That's already stated in the knowns. We have so it's 1.429 kilograms per meters cubed times 5 times 10 to the negative 5 meters cubed per second, which equals 7.145 times 10 to the negative 5 kilograms per second. To get P1 gauge, it's V2 squared minus V1 squared over 2 minus GH times density to get 301 PA. For part B, in the X direction, we need to know the angle of the spout for the oxygen tank, which is 90 degrees. So to get the X direction, we have to do in minus out plus generation, which equals accumulation. We know that it's at steady state, so that's 0. So we have the mass flow rate V1 minus the mass flow rate V2 plus P1 gauge times A1 minus Fx equals 0. Then we can factor out the mass flow rate to get this equation. V2 in angular moment, or the angular velocity, is 0.07124 meters per second. Then we can substitute that in for the velocity of V2, and we get 0.093 newtons. for the force of X. And that's it.